you work at the angle that's at the base of your result, it's easier to always work around that question.
Okay.
If you work with that one, the head, you have to always take a triangle, find the other, and work there. Because we always work, that's your sector of distance. That's theta. You work like that over there. Your variable simply equals 90. So this is your sector of 0, 90, 180 minus 9. Okay, so let's, can I draw on the paper? So now with this, the resultant starts here. Okay, imagine that's, no, that's our east, that's our west. But doesn't this result in that direction? Yeah. Right? So, okay, so. Okay, for this, that's point out here, that's more of a very constant your Cartesian coordinates. So you have a variable sum of the angle going to your result. So if you know what the new variable is, so you 124 minus the this is basically what I'm doing.
Guys, can we move on? It's already like 1 o'clock and we need to be done for this 30 minutes.
This will take 6. We are live. Should I carry it?
Cool. Guys, who's done with with the work on page 9? Okay, have you at least done the first part of finding F3? Who's found F3 on page 9? Welcome.
But I did it wrong.
But you didn't. Okay.
Are you in Boston? So, your book is there. Mr. Tegan. Okay, cool.
So guys, hello, can I get you guys' attention please? What I suggest we can do right now is, let's just carry on with Newton's. We're going to take a lunch break at 1:30, and then we'll stick around if you have any more questions. We can bomb through some questions during the lunch break if you guys want. Is that okay? So we can get through the content. Sweet. So now we're going to jump forward to force diagrams, free body diagrams, vector diagrams. So in particular, the free body diagrams. Good. Cool. So now, the key part about a physics question is getting the correct free body diagram. That's very important. If you don't get that correct, you tend to basically end up getting your entire question wrong, right? So a few things you need to ask yourself when you're now drawing the free body diagram. If you turn to page 10, just let me know when you're there. A quick yay will be yay. Awesome. Okay. So on page 10, you can see now when drawing free body diagrams, now what questions should you ask yourself, right? Now, what might be the pushing or pulling force on the object, right? Is there any friction slowing me down, all right? Is the object resting on the surface experiencing a normal force or not? what are the directions and magnitudes of all these forces? So now, if we just look at the example question. So again, just to quickly, before we do that, remember free body diagram and force diagram. What's the difference? Anyone? You're thinking vector diagram and adding vectors. But yeah, it's the one where you sort of draw the object and put all the forces on. So remember, your free body diagram, as I always say, is free of the body. It's got no body, it's just a dot. Your force diagram has the silhouette of the object. So you always think free body diagram is free of the body, it's just a dot. Okay, so now if you look at our example questions there, it says now number 1, the football is moving upwards towards its peak after being booted by the punter. Neglect air resistance, diagram the forces acting upon the football as it rises upwards towards its peak. So there's our, it's not a picture of a football, it's just a dot. So now when it's in motion, it's going on its way up. What forces do I have acting on my object? Gravity. Do I have anything else?
Force applied.
By the guy kicking it. Okay, remember in this case, it's after he's kicked it, when it's on its way up. So as it's moving, there's no force applied. The only force acting on them is gravity. Think of when you did free fall. Free fall is when you only have gravity acting on an object. It's moving because of whatever energy it has, but all it has acting on it is gravity, trying to pull it back down again. Yes? Okay. So in this case, all we'll have is F gravity. Remember now, you need to write out the full word, F gravity, not Fg. Yes? Yes?
Yes.
Yes. Okay. Number 2, a car is coasting, right, to the right and slowing down. Neglect air resistance. Diagram the forces acting upon the car. Okay, so here's my car. That was number 1. This is number 2. So there's my car. It's going to the right. It's coasting, meaning there's no engine, no brakes, nothing like that. Okay, and it's slowing down in this direction. What could possibly make a car slow down? Friction. Okay, cool. So let's first look at the forces we have. Okay, so this is my dot. Start naming forces. The obvious one that everything has, unless you're like an alien without mass. Gravity, yes. F of gravity, your weight.
The normal force.
So F gravity. Sorry, let me write this bigger. F gravity. Someone said normal force. It's a car. It's on a surface. The surface will exert a force back onto the car. We have our normal force here. F normal. Okay. And then we said, what else do we have? F applied. Do we have F applied? It's a car coasting. Like I said, there's no engine, there are no brakes. All we have is friction. What direction does friction act? Back. Opposite to motion. Sometimes, seldomly, always. Does friction?
Always.
Always. Okay, cool. So friction always acts opposite to motion. Yes? That's F for friction. Yeah. And that's that. So key thing is, remember, even if an object is moving forwards, that does not mean there's a force pushing that object forwards. It could just have the velocity that it maintains after someone like pushed it forward or something, right? If I kick a ball like the first example, the ball's going that way, there's no force making it go that way. I applied a force, I gave it momentum, I gave it speed, I gave it energy, it'll continue that way, right, until you slow it down with something else. Is everyone with me? So always just double check. Is it on a surface? Yes, then normal force. Is it an object with mass? Is it matter? Yes, Fg. Is it on a rough surface, sort of sliding on that surface, moving across the surface? Yes, friction. Right? Is someone pushing or pulling the object? Yes, there's going to be an F applied. Are there any cables or ropes sort of pulling the object? If yes, you're going to have tension force somewhere. Yes? Okay, so ask yourself those questions. The key mistake that everyone usually makes with free body diagrams and force diagrams is assuming that there's an applied force and an object's moving in a particular direction, even though they didn't mention a force pushing the object. The other mistake people make is on an incline, they like putting normal force Fg that way. And that's another big no-no again. Fg always acts vertically down. Normal force is again perpendicular to my surface. Is everyone good?
Yes.
Awesome. Okay. So now there's some questions with this stuff that you guys can practice. I'm going to quickly jump onto Newton's laws. Okay. Who knows their Newton's laws very well? Like word for word. I'll buy you chocolate at lunch if you can sort of say all three word for word. Perfect.
Can I read them?
No. Okay. So let's do this quickly. So now, if you look in your books, right, and you turn to page, so you know, 11, right? At the halfway down it says Newton's first, second, and third laws of motion and the law of universal gravitation. Yes?
Yes.
Okay, cool. So now, when we did motion in grade 10, you learned about position, displacement, velocity, and acceleration. Okay? Now, with Newton's 3 laws, first law, right, the law of inertia states that an object will remain stationary or at a constant velocity unless acted upon by a net or unbalanced force. Simply put, if there's a resulting force acting on me, I will accelerate. But Newton 1 says if there isn't one, I will not accelerate. So if I'm standing still, I'll stand still. If I'm moving at a constant velocity, I'll keep on doing just that. Colin in Cape Town, hi Colin, always likes telling the story about his kids with Newton 1. He'll say that whenever it's morning time and the kids are sleeping, time to get up and go to school, they want to stay sleeping. So whatever you're doing, they want to just keep doing that. So they'll sort of sit in bed, and it's a very hard time to get them out of bed. In the evenings, they're up there playing, having fun after dinner, playing games. Now they need to get back into bed. But do they want to get back into bed? No, they want to keep on playing. Right? That leads us to the law of inertia. What is inertia? Inertia is?
Tendency of an object to remain
Yeah.
at constant velocity or at rest.
Yeah, to sort of maintain its state of motion. So inertia basically says it's your resistance to a change in motion. If you're standing still, you want to stay standing still. If you're moving at a particular velocity, you want to keep moving at that velocity. Make sense? Okay, so it's when you're sitting in your car, and now I know men have this weird thing about them where you get to the robots and there's another guy next to you and he starts revving his car on Willem Nickel on a Sunday with the guys in the Ferraris. You hear one rev and the other guy revs as well, and next thing, boom, they're gone. And if you're sitting in the passenger seat, poof, you feel this sort of as if it's a force just pulling you all the way back. And again, inertia is not a force, very important. It's simply your body resisting the change in motion. You were at rest, perfectly fine, robot was. The car decides, I want to go off at 200 kilometers an hour. Your body says, no thank you, I want to stay right there. And then as the car goes forward, you sort of feel this motion there, and it's not you being pulled back, it's you staying behind as the car goes forward. Yes?
Yes.
Fantastic. Newton's second law. Newton's second law states now, remember, Newton's first law says, if you don't apply a net force onto me, I will not accelerate. Newton's second law says, well, what if there is a force on me? So that is now, in this case, if there is a force, what will I do? I'll accelerate, right? So if a net force is applied onto an object, the object will accelerate in the direction of that net force, right? The acceleration will be directly proportional to the force applied and inversely proportional to the mass of the object. Simply put, that whole long statement just says this. Okay? So if a force is applied to an object, the object will accelerate. The acceleration will be directly proportional to the force and inversely proportional to the mass of said object. Simple, yes? Okay, cool. And Newton's third law states that if object 1 applies a force to object 2 will apply a force of equal magnitude simultaneously back onto object 1. The forces will be equal in magnitude but opposite in direction. We call that an action-reaction pair, right? So now, quick question, does it, like, if I apply force to you and you apply the force back to me, do our forces cancel out?
No.
Why?
Because they're acting on different objects.
Thank you. So the forces will only cancel out if they're acting on the same object. Okay, now I'll give you my quick synopsis of Newton's 3 laws. Newton 1, if you don't push me, I will not get angry. That's acceleration, by the way. So if you don't push me, I won't get angry. Newton 2, if you do push me, I will get angry. Newton 3, if you push me, I will push you back. Plain simple, you'll never forget that. Yes? Okay, Newton 1, if I don't push the object, it will not accelerate. Newton 2, if you do push the object, it will accelerate in the direction that you're pushing it in. Newton 3, push an object and it will push you back. Yes? Fantastic. Okay. Now the one thing I want you guys to quickly remember, applying Newton's second law, people always tend to sort of, that's F net is equal to MA. They get stuck and say, well, F net is equal to MA, and then when you have to apply it, they're like, well, what's my F net? Keep in mind, F net is simply the sum of all your forces. So if you've got several forces, that's just going to be F1 plus F2 plus blah, blah, blah. All the forces you have acting on the object, right? Provided they're in the same direction, again. And that will be equal to your mass times the acceleration of your object. Simple enough? Fantastic. Okay. Now I want us to turn to page... Sorry, I forgot the Newton's gravitational law. So again, Newton's gravitational law again. Everybody in the universe attracts every other body with the force that's directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So basically what that's saying is there's an attraction between any two objects that have a mass in the universe. Yes? So I'm attracting that table, I'm attracting this board, the board's attracting me, I'm attracting the building's attracting me, I'm attracting the earth, and the earth is attracting me at the same time. Right? We normally don't feel all the other attractive forces because the force of the earth on us is normally so huge that it really doesn't make much of a difference. I had a chat with Dylan yesterday about we have the earth attracting us and we can feel that as our weight, right? As sort of our attraction. When you jump, you're going to come back down again. Jump off a building, you're not going to fly, you're going to go straight down again. Okay? Now, the sun is so much bigger than the earth. Why is it that we aren't sort of floating off and just going towards the sun if it's that much bigger, if it weighs that much more than the earth? Thank you. The distance, right? So the distance between us and the sun is very, 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 very vast. So basically, if we look at the force of the sun on us, it's so small, it doesn't even compare to the force of the earth compared to us because we're so close to the earth. So always remember, it's not about the masses only, it's about the masses and the distance between the two objects. And remember, the thing is, it's the square of the distance between the centers of the object. So the further you are, the weaker the force gets exponentially because it's divided by r squared. Remember the formula? Your force of gravity is equal to capital G, the constant, times m1 times m2 divided by r squared. So see, this is an inverse proportionality, a square one. The bigger this gets, the smaller this is. And this is always squared, so it gets sort of smaller exponentially. Okay, sweet. Let's quickly look at the example question, right, on page 12. On the left-hand side, you've got definitions. On the right-hand side, you've got terms that match those definitions. Are you guys there? If you're there, give me a quick yay. Yay. Thank you. Cool. So now, if you look on the left, definitions. A combination of all the forces acting on an object. Could that be either inertia, unbalanced force, friction, law of inertia, mass, or net force? Hands up for net force. Yes, it's net force. Okay. 2, the force that opposes the motion of any object. Is that inertia, unbalanced force, friction, law of inertia, mass, or net force? Yes, friction. Remember, like we said, friction opposes the motion of objects. Sweet. Any questions? None? Cool. 3, an object's motion will not change unless an unbalanced force acts on it. Which one is that? Hands up for inertia. Other hands up for law of inertia. There we go. It's the law of inertia. Okay? Thank you. And then number 4, the factor that determines the inertia of an object. What is that? The mass of the object. Well done. And then number 5, type of force needed to overcome inertia of an object. B, unbalanced force. Well done. And 6, the tendency of an object to resist a change in motion. A, inertia. Well done. That was quite quick. Okay? The other one, now state whether the following questions are true or false. The relationship between mass and inertia is described by Newton's second law of motion. False, because it's the first law, right? Yes. Number 2, the greater the net force applied to a given object, the more it will accelerate. That's very true, yes. Your weight equals your mass multiplied by the acceleration due to gravity. True. The next one, forces always act in pairs. That is false. Number 2, action and reaction forces always cancel out. That is true. 3, action and reaction forces... Sorry. My mind was sort of just going in this rhythm. Sorry, okay, cool. Action and reaction forces always cancel out. That is false. Right? I was saying true to your false. Okay. 3, action and reaction forces always result in motion. False. Okay. And then jumping to the next page, okay? So we're going to answer the following questions. They're very, very basic, okay? So now it says, what net force is required to accelerate a car at a rate of 2 meters per second squared if the car has a mass of 3,000 kilograms? So look at, okay? Yeah. F net is equal to my mass times my acceleration, right? We're looking for the net force. The mass is 3,000 kilograms. My acceleration is 2 meters per second. Yeah? That's going to give us 6,000 newtons in the direction of the force. Simple enough. Hello?
Yeah.
Yes.
Okay, awesome. Now, what I want us to try, can I raise the board?
Yeah.
Okay. Now, I want us to quickly try an activity, question 2. It's titled Studying Like a Boss. Okay, that's how you guys speak now. Josie, I don't know how to pronounce this name, Matisha, at a study session and wanted to suspend a lamp from a hook in the center of the room, but they want the lamp to hang to the side of the room out of the way. So they attach the lamp to a ring P, as in the diagram, which is attached to the ceiling, but also pulled to the side by a string A, as shown below. To keep ring P pulled to the side, they attach a string A to hook to the brick, which they place on top of the bookcase, which has a rough surface. Okay, so we basically have now our lamp posted somewhere there, that's attached to the ceiling, and they pull that to the side by attaching it to a brick and placing that brick on a bookcase to the side there. Does that make sense? Okay, so we've got the string C attached to the lamp, string B attached to the ceiling, and string A attached to my brick there. And in the center you've got a ring labeled point P. Is that too small?
No.
Okay, but you have the diagram in your books. I'm just sort of redrawing it there. Yes?
Yeah.
Okay, now let's look at 2.1. Represent the forces acting on the ring P using a closed triangle, labeling each force and two known angles in the triangle. Okay, so if we look at that, let's draw point P like that and put all the forces. So string B is going to be pulling point P that way, correct? Okay, and string A is pulling point P this way, correct? Hello?
Yes.
Okay, string C is pulling it downwards. Okay, so I'm going to start by doing this and saying, well, B is pulling that way, C is pulling this way, and A is pulling that way. Now what they want from us is a vector triangle, which is like our vector diagram. We need to put these all head to tail so that they match up quite nicely. You guys with me? Okay? So what I can do now is I can take A and draw A there. I'm going to take C and put it at the end of A. Down like that. That's C. And then B will start nicely at the end of C, coming back towards A.
How do you know that A and C are at a right angle?
Because the lamp is hanging vertically down and A is horizontally that way. Cool.
Do you draw the tail at the end of the arrowhead or on the line?
What do you mean?
So when you're drawing the triangle,
Yeah.
do you draw the end of the...
Oh, so I think, do you draw it there or there?
Yeah.
At the end of the arrowhead,
Okay.
at the very tip. Okay. Let's fix my arrowhead here. This was a very ugly one. Okay. Does everyone get how to draw this? Just take your vectors, put them head to tail, and it'll work out to a beautiful vector diagram. Okay. If my vector diagram looks like this, if it forms what we call a closed loop, what does that tell me about my resultant?
Equilibrium.
Yeah, equilibrium. I've got a zero resultant. Cool. So now, that's 2.1 done. Okay. 2.2. Given that the mass of the brick is...
It also asks two known angles in the
Sorry,
triangle.
thank you so much. Okay. So we know that the angle between A and C is 90 degrees. Yeah? That's that one there. And we see that the angle between B and the horizontal is 30. Yes? So if there's B, there's my horizontal. If this is 30 degrees, what's going to be here? 60 degrees. And we can, just to make sure we get all our marks, we can work out that one and say, well,
Could you
Yes.
not do it? They gave us the 30.
yeah,
Could you not do it the other way?
which other way?
So you know that A is the horizontal,
Mhm.
and you know that it's to B, to 30.
Yeah, you can do that way as well. Okay. Sweet. Is everyone with me? Thank you. Okay. 2.2, given that the mass of the brick is 1.5 kilograms, calculate the magnitude of the maximum force of static friction that the brick can experience before slipping. The coefficient of static friction between the brick and the bookcase is 0.6. So 2.2, you're looking for Fs max. Yes? Hello?
Yeah.
Cool. That's our static coefficient of friction times our F normal. Okay? Our coefficient of static friction is going to be 0,6. What's our normal force?
Opposite of C. What's the weight?
Normal force of the, what's the mass of the brick? It was given that 1.5 kilograms. Right? Yeah. So our normal force will be equal in magnitude to our gravitational force of the brick, of the earth on the brick in this example. So our normal force will simply be 1,5 times 9,8. Yeah? Hello?
Yes.
Yay. Answer. Fantastic. 8,82 newtons direction. Upwards. Okay, it's very important, guys. Never forget your direction. You guys lose lots and lots and lots of marks by forgetting direction. Okay. That's that one done. 2.3. Using your answers in question 2.1 and 2.2, calculate the magnitude of the maximum weight of the lamp that can be supported in the setup without the brick sliding. Okay. So now when we look at this, if the maximum weight that sort of A can hold before the brick slides should be equal to my Fs max. Yes? Okay. So meaning if we assume now that the force in A is equal to our Fs max, we're going to now try find C. Correct? How will we do that?
Wouldn't it be the same as the y component of B?
The y or x?
The y.
What's the same as the y component of B?
C.
Oh yes. Okay. I thought you were talking about I was talking about A.
No.
Okay. That's fine. So the key thing is we know what A is. We're going to use that to find the x component of B, and then once we have B, we can find the y component of B, which will be equal to C. Yes? Okay. Is everyone with me?
Yeah.
Everyone gets the explanation?
Yeah.
Fantastic. Okay. Sorry. Thanks for that. I was thinking normal force. It's to the left. I was thinking up because of normal force. Sorry. Yes, it's to the left. Thanks so much. Okay? No, it's your frictional force. Because the string is trying to pull it to the right, and friction's got to act against that motion, to the left. Does that make sense? Everyone with me? Any questions? Nothing? Okay, cool. So now, 2.3 quickly. So we know that the tension in A, right, is equal to our Fs max, which is 8,82 newtons. Just in this case, it's going to be to the right from that point there. Yes? But if we're looking at the tension from point P, it'll be what direction? To the left, right? Okay. So remember, tension works depending on your point of view. If I'm holding a string with someone there, and I'm on this side, the force is going that way. Someone is standing sort of here, and they're holding the string here, it's pulling that way. Yes? Okay. So if we're looking for tension in A, looking at point P, it's going to be 8.82 newtons pulling that way. Yes? Okay. Then with that, we can then find our B. Yes? Hello?
Yes.
Okay. So we can then find our B, and using B, we can then find C. Or what's an easier way?
There is?
Making a diagram.
Because the string is pulling the brick that way. So the friction's got to counteract that by pulling that way, to the left. So my string's pulling me right, I'm going to counteract the friction by sort of pulling left. Does that make sense? Okay. Why did we draw this? Yeah, we can use a triangle to work out C. Because we already have now tension in A. That's tension in A there. We can use this triangle to work out C. Without having to sort of first go A, and then B, and then C. We can just use this because this gives us our relationship of all the three vectors. You guys with me? Mm-hmm. Fantastic. Okay, cool. So now, in that case, to work out B, we're going to use our trig identities. Okay? So we want to work out C. So we want C, we've got A, we've got angles over there. So if I say tan of 30 should be C over A. Yes? Yes?
Yes.
You guys with me?
Yes.
Someone say no.
No.
Okay. So tan of 30 degrees should be equal to my C divided by A. Yes? Therefore, working out C, I'm going to multiply both sides by A, and then I'll just get C is equal to A times tan, 38. Tan 30 degrees. And then I can plug in my value for A, which is 8, comma 82 times tan of 30 degrees. And what's the answer that I'll get? 5,09 newtons. Direction? Hello? Downwards. Okay, cool. Okay, and that is equal to my FG of whatever object's gonna have I'm gonna have at the end of C. So like my lamp in this case. Yes?
Yeah.
Yeah.
Okay. Is everyone with me? Okay, 2,4. Calculate the magnitude of the tension in the string B when the lamp has a maximum weight as calculated in question 2.3. And then we can do the exact same thing we were doing before. So we now know this, we now know that, we can just use Pythagoras to get B. Yes?
Yes.
Thank you. 2,4. B squared is equal to A squared plus C squared. That's going to be my A, we said was 8.82. My C, we said was 5,09. Squared, that's B squared. We root this and we root that entire thing there. B then becomes, what's the answer for B?
10,2.
10, 2 newtons. Direction? Hello?
Yeah.
Just no.
60 degrees east of
Do we need to find that? So what's the magnitude of the tension? So if they say magnitude, don't even worry about the direction. Don't do all the extra work, you're going to sort of waste time in your test. Okay. Newtons, and that's perfect, that's all you need. Does that make sense? Okay, any questions? None. Sweet. Can you guys please now start off back on page 13, the second part. Now question 2 of just above activity questions, and then you can do 1.2, basically the questions we have from page 13, the questions we haven't done. So 1.2 of the activity question, and then the question 5 that follows the one we just did now. Afterwards we can take a break. Okay. It's a very short question. Okay. If you have any questions, Dylan's there, Robin's there, I'm here, and we'll answer your questions. Sweet.